Okay, hello everybody, welcome back. I've been looking at my schematic here on the Schmidt trigger circuit that we did last night, and I'm not happy with the performance of this circuit, and I'll tell you why. Whenever I go to advance the input, number one, it jumps up too fast like that. Okay, it jumps up fast, but here's the thing that I don't like about it. When I'm running the motor, as I keep on advancing the input voltage on a square wave, watch what happens. I get so far, and then all of a sudden, it jumps just like that into high DC output. That's not right. That shouldn't be doing that there. That should not be. That should be going a very smooth transition, and it's not. And that causes the motor to jump in voltage also, which is not good. And I knew something wasn't working right here. So I went back and I looked at my calculations, and I realized I did something here on my calculator. Right here for RC1, it says 0.1 volts divided by the base current 2 that we had here of 1.3 milliamps. Well, when I inputted that into my calculator, I didn't hit the percentage button, or not the percentage, the decimal button hard enough, and it didn't take it. So instead of getting, I got a value of 750 ohms here. When I went back and did this calculation here, it ends up being 75 ohms. So when I change this to 75 ohms, watch how it works now on the circuit. I change this to 75 ohms right here. Okay, let's watch the waveform now as I advance to input voltage. See how I get a nice transition coming in there, very nice transition on the start, and now it increases. Now it's a nice transition all the way around. Now when I get to the top here, it's a nice transition. Look at that, nice smooth transition going right up into the DC voltage. It's not jumping, it's giving a nice transition. Now, let's go ahead and run this on the motor, and let's watch the performance of the motor now. It's going to be a lot different now, too. So I'll hook the motor up here now, and we'll go ahead and turn this on now. Boy, that's a nice transition. Look, I got this going really, really slow here. And now we'll go ahead and watch the motor here while I turn this up now. Now it's full speed. Right now I have it, it's not jumping. Right there is full speed, and look, I can just take it down real slow now. Back up a little bit, back and forth. It's working really nice now. Full speed, and I can slow it down. Go full speed again. So you can see how the transition is nice and smooth now. Now all that is a result of just one resistor value that was not calculated properly. Changing that resistor made the circuit work perfectly now the way it's supposed to, and I'm very satisfied with that. And what that shows then is that we just can't throw resistors in here. We have to use Ohm's law, and we have to use different kind of sequence of operations here to be able to get proper currents and voltages where it's needed. And that's a good lesson learned right there. Also, make sure I'm hitting the right keys on my calculator too. Okay, so now we're ready to continue on with the rest of the circuit now. Okay, continue on with the circuit here now. I've been looking at this here, and I found out that whenever I remove the power from the entire circuit, that the capacitor bank on the 18 volt side here, that discharges really well through here, but the 80 volt side does not discharge at all. And the reason why is because when I disconnect the power, the motor has no way of discharging the capacitor bank for 80 volts because it's no longer connected to ground. So what I'm going to need to do is I'm going to need to put a resistor right across the power supply itself here that's going to drain a very low current drain. And I'm going to look at 100K here first, and I want to check some calculations here and find out if a quarter watt 100K resistor will work for this. So in order to do that, we use the equation for power. Power is power equals voltage times current. And what I want to do is I want to look at what the power would be across this resistor. Power also is voltage squared. divided by resistance, and that's what we're going to find out here. We're going to take 80 squared and divide that by 100K and see if 100K, a quarter watt resistor is going to work for that. So I go over here and I'll go with my 80 volts squared divided by resistance of 100K, and that gives me 64 milliwatts. So 100K 250 milliwatt resistor will work fine for this here to put across there, and then we can start continuing with the rest of the circuit. Okay, so one more thing I want to do is we want to see how much current drain that's going to have. So we're going to use again 80 volts divided by the 100K ohm resistor. 1, 2, 3, 4, 5. Okay, that gives us about 800 microamps of current drain. 800 microamps will be draining off that there 80 volt supply every time I turn it on, and that should be okay. Okay, now we're ready to start working on a torque feedback. Now when there's a load on the motor, that impedance goes down. That's going to cause the ground to be more present here, and so we're going to have some electron current here that can bleed off here in this direction here, and we can tap it right here, and we're going to, because there's going to be a very small current that we're going to be amplifying here, we're going to have to take it through about a couple stages of amplification here. So we'll put an input resistor here, and because this is electron current, negative charge, we have to take this into the base of a PNP transistor. Now this PNP transistor, its emitter is going to go back to the positive side of the battery of the 80 volt side. So because of that, I'm going to have to use a tip 42C, a power transistor for that one, only because it's going back to the 80 volt rail. The collector of this transistor then will go through a input resistance here into the base of a NPN transistor. The reason why we're doing it this way here is because we need to get a couple stages of amplification, because of the current that's going to be bleeding off here is very small, and so we have to get enough amplification here so that we can return that signal back with a strong signal back to the input again. Okay, so let's go ahead and build this part here, and I think on this NPN here I'm going to go ahead and put a bring the emitter down to ground, and I'm going to use an indicator LED here, and I'm going to check and see if this LED lights up. If it lights up okay, then I know that we're getting signal through here, and that's what we're going to check here now. This LED is going to be used as an indicator only right now, just to check the signal. Okay, I'll go ahead and build this now. Oh, by the way, for these here input resistances here, I'll have to experiment to see which I need. I'm going to start out with 10K on both of them, and then I'll just experiment until I find what I need. Otherwise I'll have to do some calculations, current calculations, and I may have to do that too. But I'm just going to put two 10Ks in here right now and see how that works first. On this here indicator LED here, I'm going to return that with a resistor. I'm going to return that back to the 20 volt supply, because I can that goes back to the positive side of the battery here on the 20 volt supply, and that way I can use a smaller resistance here and won't be using any kind of power resistors. Okay, now I'll go ahead and build this and see how this works. Okay, putting a 100K ohm resistor in here and throwing one in here is not going to work in this, because we are now in an area where we have to bias this transistor on now into a linear region. What's happening right now is we're in cutoff, and it's taking a very small current here to cause any kind of a transistor action in here. The LED lights very, very dimly, and it takes a lot of motor current to make this light up, which means is that I have to get a voltage reading here under normal idle conditions, and then I got to put start putting a load on the motor and checking to see what this voltage comes out to, and then I have to adjust the resistances here and make a voltage divider and put a voltage at the base of this transistor here that puts it in a linear region so that it responds to a change in voltage here. And that's where we're going to start getting into some heavy calculations now and some thinking process here of how to design this to make this compatible with this now. And that's coming up next. We're going to get some measurements here now. So under no load, the supply is about 84 volts. That's the motor supply with no load on the motor. and with the motor off condition. So we actually have 84 volts with the motor not running. Now we're going to take a measurement with the motor running at a very slow speed, and we'll take a measurement now at the motor itself. Now we're going to take a voltage reading here, and we're at 83.1 volts. That's at this point right here now. So under very small low conditions here, we're at about 83.1 volts. We're at about 83 volts here. It drops about 1 volt. Okay, so we're at 83 volts, very slow. Now we'll speed it up all the way to the full. Take a measurement, 81.5 volts. Okay, so we go from 83 to 81. Okay, in that area there. So now we want to design this here voltage divider here to put this transistor base at about 83 volts. We're going to make this has to be a little bit more negative, so we're going to have to work on that there and get that there to that value there. Okay, doing some calculations, I found that if I put an 820 ohm resistor here that feeds in from the motor current into the base here, and then I put a bleed-off resistor here to ground of 68K, that would bias the transistor into the conductive region. I found out that it's just, and I use a 100K ohm resistor going into the base of the into the NPN transistor here that is driving the LED. I found out that by doing that there, that I am driving this PNP transistor on too hard with the 68K. So what I was doing is I'm using my resistor substitution box here, and I'm just switching in resistances here to the base of this transistor here to bias it on, and I'm looking for about 240K way it looks, and that seems to work pretty good where the light comes on and goes off like it's supposed to, and then whenever I put a load on the motor, I get the LED light lit up like it's supposed to be. So doing some experimenting here, I found out that if I use a 220K to ground here and then use these resistance values here, it should work pretty good. Okay, I said 220K, but it's actually 240K. That's what I need to use to put in here now. So I'm going to put that in there and see how it works. Okay, that's working really good. As I increase the input voltage, the light will come on because the motor is speeding up. But then once the motor gets enough speed, the resistance goes up again and the current goes down, and then the light drops back to normal again. And that's what we want right there. Now I'm at full speed, and see how it's back to normal again. As I decrease the voltage on the motor down to 0 here, now as I increase it again, that's an indication that the motor is getting an increase in current as I keep on turning the knob here. But as long as that light keeps on dropping back to normal here, then this is working properly. So let's go ahead and put it down to very low voltage now, very low input here to the motor, and we're going to see if this light lights up okay now. Okay, so I now have it going very slow here, and let's take a look at the light now. I put a load on here. Oh, that's nice. I'm now stalling the motor, and the light's coming on, which is working good. I stall the motor, and the light is coming on. Okay, that's working good now. Okay, now we can proceed to the next part of the design.